Okay, so let's continue from last time. We discussed how we can minimize the loss function using the stochastic gradient descent algorithm. The algorithm gives updates for the weights or the parameters of our neural network. So to recap, given our previous or old parameters, the algorithm updates them using some learning rate. The steepest descent of or the fastest way that these parameters can be updated and give us the next best parameters. So here we want to zoom in into this gradient term. Like I said, this gives us the direction for the fastest decrease of our loss function. And to compute this, we need to compute how sensitive is L to changing each one of these parameters. So here I assumed I have n parameters in total, which of course includes the weights and the bias parameters. So now the challenge is how to effectively compute these terms for potentially millions of parameters. Calculating this naively will be very expensive. Here we introduce backpropagation that allows us to compute these weights very efficiently. So before going into the algorithm, let's recall a basic rule in calculus, the chain rule. So to do that, let's consider with a very simple case of a single neuron that has an input AL-1, or the activation from the previous layer, that multiplies with the weight that connects that node to this. This will go through an activation function, and after that, that will give us the value of the neuron. Recall that we had the bias term here that I melted to be inside this W's. So I'm going to, just to simplify my notation, I'm going to melt this into the weight, which of course means that I'm adding a term 1 here to this vector. So with that setting aside, now we have an input from the activation from the previous layer multiplied by the weight. And then that goes through an activation function. Then after that, we have the activation value for the neuron that we are focusing on. So to simplify the notation, I'm going to introduce an intermediate variable here, which is basically the value before the activation. So if I write it down, it's basically CL is the value of previous layer multiplied by the weight. And of course, like I said, the bias term. So the value of my neuron is the value of CL going through the activation function. So now let's assume this is the value of the output value of the neural network, and we are comparing this against reference signal Y, and we have a loss function. Let's assume that loss function is a simple quadratic loss, and we basically want to know how we can change the parameters of this neural network here in a way that minimizes the loss function, right? So we want to compute the changes of the loss function with respect to changes of our parameter here, which is W of L, layer L. So let's write this down in a chain rule. So first, we have the gradient of L. So first, we are looking at the changes of L with respect to the changes of the value of neuron at the layer L, and to write the rest of the chain, I'm going to write the changes of the value of L with respect to the value of this intermediate variable that we introduced, and then the changes of that intermediate variable with respect to the changes of W. So basically, this means that if I change the knob, if I have a knob here, let's say, if I change the knob for W, how much it changes Z, then with the changes in Z, how much it changes A, with the changes of A, how much it changes L. So that's how we are basically turning the knob here for W, and then that's how we are adjusting L. And in this case, our optimization want to, of course, reduce L, and this basically gives us the gradient. So at the end of the neural network, when we are computing this loss, this error is obvious. So we want to tell the neural network, and we want you to reduce this. So basically, we want to blame the neural network in a way that the neural network does something to reduce this blame. So the blame is obvious. What's the blame at the end is basically this error. But it's not that obvious. What is the amount of blame for different components of the neural network? For example, for a deep neural network, how much of the blame is for a weight at the early stages or early layers? So basically here, what we are doing is to send or propagate this error or this blame backward when it's obvious to when it's not so obvious. And basically backpropagation is doing this. It backpropagates this error to the earlier components of the neural network. So let's formalize this game of blame. Let's start with defining intermediate quantity. And this quantity, delta, for the layer L, so an arbitrary layer L, is basically the blame signal for layer L. We define it basically to be this. This means how much did the pre-activation value of each neuron in layer L contribute to the final loss. So let's start the game from the last layer. The last layer is L, right? So the blame at that last layer is written this way. So for a simple squared error loss, so we can, of course, if you remember our notation here, we can write this down using our chain rule, and it will be like this. Multiply by the sensitivity of the activation function, right? So when we have vectors here, so this will be a vector, and this will be, of course, a vector because we have multiple weights that goes in. I'm going to write this element-wise multiplication using this notation, which is known as Hadamard multiplication. So we simplify, because we know everything is vectors and matrices, of course. So let's drop that arrows. In the case of the simple squared error loss, if you remember, this is basically this, which is literally the error, right? So this blame at L is the error, and scaled by the sensitivity of the activation function to its input. Once we know the blame layer L+1, we want to backpropagate it to the previous layer L. So we have to multiply this blame by the weights that are connecting the two layers, which is the weights at layer L+1. Like I said, this is a vector, so we have to take care of this. It's not a scalar anymore, so there is a transpose here. And of course, we are sending this to our activation function. So what does this equation tell us? Basically tell us that the blame at layer L is the blame from the next layer propagated backward through the transpose of the weight matrix WL+1 and then scaled by the local gradient of the activation function at layer L. This allows us to move backward through the network from the last layer to the previous layer and so on and so forth until the first layer. Okay, so now we have the blame signal for each layer. So the gradient for the weights of any layer L that we write this way can be found directly using this layer's blame signal and the activation from the previous layer AL-1. And it's simply the product of these two. And this basically gives us the update that is proportional to the blame signal and the signal that was flowing through the weights during the forward pass. So believe it or not, we are really done here because this recursion basically gives us the update for all the weights and of course biases. So that's the elegance of this matrix vector notation. For example, here, I could open this up and write it this way, right? This is a component of this vector here is actually the blame signal for a neuron J in layer L, right? That we could open this up in its really summation form, which is the equivalent form, which gives us the weights, the sum of the products of the weights and blame from the future layer, right? So this is basically a sum multiplied by the sensitivity of the loss function. So instead of writing it this way, we wrote it this way. It's the same. So basically this matrix vector product really performs all the necessary summations that we need. So let's, even we can look at another example. So I said that we compute the weight gradient, and this here is an outer product that computes the entire gradient matrix in one step. How does it work? This is basically here, this is a column vector, let's say of shape m/1. I basically want to say that if I have a layer with size n, so this is the layer L, if this one has m neuron, we want to backpropagate the blame from this to the previous one, right? And we multiply by the blame signal from L by the activation vector from the previous layer L-1 that is also a column vector but of shape n/1. And the transpose will be 1/n. So this multiplication here gives us a matrix of m/n, which is basically a matrix with entries like this. So this resultant m/n matrix is the exact same dimension as the weight matrix WL, right? So the resultant m/n matrix has the exact same dimension as the weight matrix W at that layer, right? So an element is basically the blame from neuron I multiplied by the activation from neuron J. So the beauty of this formulation is not just, of course, for cleaner notation. it maps directly to how our modern hardware, like our GPUs, perform computation. Matrix multiplications are highly parallelizable, making this backpropagation algorithm incredibly efficient on a large scale. These two equations describe the learning process for a simple network with a handful of neurons, and also the same equations describe the learning for a massive foundation model with billions of parameters. Like I said, the logic of propagating this blame remains identical. Only the sizes of the matrices really change. So let's look at what does this algorithm do. It basically it's just a chain rule that compute the gradients efficiently. It works in two passes. There is a forward pass that computes the activations and store the intermediate values. There is a backward pass that compute gradients by propagating errors backward. That means that it computes all the gradients in one backward pass, and it reuses the intermediate computation. And also, of course, it exploits the structure of neural networks. The error signal delta L basically summarizes how much each neuron contributes to the overall loss, and the whole process really is in the complexity is in O of n. If you remember, n is the number of parameters of the neural network. So it linearly scales with the number of parameters. Okay, so that's it, really. We have everything we need. So now we can zoom into techniques and how we can do this training in a way that gives us the best result for our learning problem. So one obvious thing that maybe it's evident from here is the importance of the activation function, right here. This sigma prime of ZL basically tell us the sensitivity of this activation function, right? How sensitive it is to the value and the changes of these values in intermediate layers. In other words, it's like a gate that controls how much gradient is allowed to flow backward through each neuron. So the value of this derivative somehow determines if the gate is open, closed, or somewhere in between. And this gating mechanism is critical for understanding why some activation functions are preferred over others in deep networks. For a long time, a common activation function was a sigmoid function that basically it squishes all real values into a range of 0, 1. You can imagine the plot, and it's fairly easy. It's basically a function like this that is between 0 and 1. And the important thing here is the derivative of this function takes its maximum value when z is 0, and this maximum value at z0 is 0.25. So it's always less than that in other points. And when the input is farther from 0 to each direction, it actually, the sensitivity becomes 0. So what does this mean? This means the sigmoid gate is at best only partially open and is often nearly closed. So in a deep network, these small derivatives that are multiplied together at each layer, if you remember from the chain rule, this causes the gradient to shrink exponentially as it flows backward. A famous problem that is known as vanishing gradient. This makes the signal the gradient signal that comes from the last layer to be very weak, and it cannot update basically the early layer efficiently. You already know the other option that we looked at, and it's the rectified linear unit, or in short, ReLU. So ReLU is basically, it takes the maximum of the signal or zero. It means that whenever the signal is negative, it basically returns zero, and when it's positive, it will return the value of the signal. This is basically, so what will be the derivative of this function? We can write it this way. So notice that I said the derivative is 0 at 0, which is not really true because it's not differentiable at that point. But we really don't care because the probability of the value of z falling at exactly 0 is almost zero. So that's why we just correct that issue, and we just put 0 here. I mean, even if we had this, if we push that probability to be 1 at 0, doesn't really matter, like I said, because it's very improbable for z to fall exactly at 0. So the behavior of this ReLU gate is very simple. It's either fully open for value of z that is positive, or it's fully closed. So the consequence is, if a neuron was active during the forward pass, in other words, the value was positive, the gradient passed through it unchanged during backpropagation because of the multiplication by 1, right? And this allows the error signal to travel back through many layers without diminishing. It acts like a gradient superhighway. And this is a reliable gradient flow. And the reason is primarily because of the ReLU and other variants of ReLU that basically that are mostly default choice for most deep neural networks. So let's continue on this conversation. We discussed the importance of this activation function and its sensitivity in allowing for the gradients to go deeper in the neural network. And there are many other techniques that help us do a better training of neural network and making sure this forward and backward pass will give us the best result for the specific data that we are dealing with and the amount of information in that data that we want to pass forward and the amount of information of the error that we are receiving from the supervision signal backward. So this forward and backward passes, we want to make sure that we are controlling these signals in both ways, in a way that we can reach deeper in the network from both sides. So for example, one thing that we really didn't discuss much, but we saw its importance in the stochastic gradient descent lecture, is how to initialize the weight, where to start our search in this gradient surface, and how to find the optimum point from an initial point, how to set this initial point in a way that gives us the best basically promise for success. So far we just put an initial weight to be random, right? So for example, some very small value scaled by a random scaling factor, right? So this way we prevent the weights from being too large, right? So like I said, a neural network is a pipeline of sequential computation signal, which in the forward pass is the activations, and in the backward pass are the gradients. The signal travels through this pipeline. The variance of this signal, we can think of it like the energy of it. It's important to control how it flows in these two directions. If the variance increases layer by layer, the signal can grow exponentially until it becomes enormous. Or in your Python languages, it becomes nans. And this basically leads to exploiting gradients. This exploding gradients renders a useless model. On the other hand, if the variance decreases layer by layer, the signal then shrinks exponentially until it becomes virtually zero. This again leads to vanishing gradients, where the early layers of the network receive no learning signal and their weights are never updated. So let's think about ways to start this strategy from a good point. So what is a good point? One measure is we want to somehow keep the variance of both the activations and the backpropagated gradients. So this is a good rule of thumb, right? We can at least initialize the weights in a way that we ensure the variance at the beginning is constant. So let's zoom in into this. To analyze the variance of single neuron's pre-activation value, or Z, we can basically write it this way. So Z, as you remember, is the sum of all of these inputs xi weighted by wi's. So at the beginning, we assume these two are independent and identically distributed. It's a reasonable assumption at the beginning because we haven't done anything yet. So we choose them in a way that, for example, this independence happen, and this pure random will give us that. And then we scale the input data, for example, to be to have a mean 0. And we can choose the initial weight to have mean 0 too. The scaled input data can also have variance 0, because that's how we are dealing with our data, pre-process our data before feeding to the network. And here we want to choose the variance of W. So now let's look at the variance of Z, given these two choice, right? So the variance of Z can be written this way, like I said, because of all of this nice independence at the beginning, which basically means that the variance of Z equals the number of weights or parameters, and variance of W, and variance of X. We know the variance of X is 1, and this basically means that to have a variance of Z to be 1, it's enough to have a weight distribution that has a variance of 1n, right? So this was for the input, when we have an input with mean 0 and variance 1. And this choice of W ensures that the energy of the input signal will remain the same when it goes in the forward pass. So here in this forward pass, by n I mean the number of inputs to the neuron. Sometimes we call this n subscript n. Or in other words, in some circles, they call it a fan-in of the layer. So this logic, like I said, will ensure the forward pass is stable. But how about the backward pass? So if we want to do the same thing for the backward pass, we want the variance of W to be 1 over n out, right? And like I said, for obvious reason, we call this fan out. So how to make sure we satisfy these two? So one way to do it, which is very common in the activation functions that are symmetric, for example, the sigmoid or tangent hyperbolic, we can easily use the variance of W to be 2 over 1 fan in plus fan out. So that's great. This is known as Xavier initialization. And this is actually very common in training neural network. This is a very common choice when we have this type of activation functions. But what if we don't have a symmetric activation function? And a very common and friendly example is ReLU. So in this case, we only use a fan in for our choice. So notice that this is the variance is half from the previous case, and the reason is basically ReLU effectively discards half of the input distribution because of all the negative values are 0, and this way the variance will be half. And then the other thing is we only used fan in, and the reason is because the ReLU networks are more sensitive to this value, and it's enough to consider that. So how we can choose weights to have weight distributions to have 0 mean and this variance? One way is to just use a normal distribution, right? So a normal distribution for weights that follows mean 0 and one of these variances, right? For example, in this case, we have this normal distribution. So to wrap up, because ReLU activation functions are very common, it's often the default choice to go with this, and this is also known as He strategy or initialization strategy. So to summarize, it's very important to ensure that the energy of the signal and its variance does not die out or explode as it travels through the network. You will see that PyTorch, for example, a modern framework, will use these methods when it initializes the weights of the neural network. And the difference of doing this or not is the difference between a smooth or a stock training, or basically a gradient that flows nicely or vanishes or explodes, and the conversions that can be fast or slow or even no learning. So we discussed this weight initialization. It can give us a good starting point, a starting point that is stable, but as the training progresses, the weights will change. They are constantly updated, and the distribution of each layer's input can shift and change. This is a common problem, and the issues that we discussed, including vanishing and exploding signals, will and can repeat in this process of the training. This is a very common issue, a phenomenon that is known as the internal covariate shift. And the idea is the distribution of each layer's input changes during the training. And this complicates the learning of subsequent layers. There are lots of techniques that are devised to deal with this issue. Some that are more common we will discuss in this lecture. But of course, there are other techniques that can be tailored for different architectures. So we will start with a very common technique that is considered foundational when we are dealing with a mini batch training, and the mini batch is rather not small, and it can be reliably large, and we can use a batch normalization. So batch normalization is basically a way to normalize the pre-activation values in the network. So it is inserted at before the linear layers and before the nonlinear activation functions. Hence, they are getting the value z. And how it works is basically for each mini batch during training, batch normalization first calculates the mean and variance of these pre-activation values, these z's, and then normalizes them to have a mean 0 and a variance of 1. The normalized z can be written this way, where mu b is the mean and sigma 2 b is the variance of the current mini batch b. So epsilon is a constant just for numerical stability. This basically gives us somehow counterintuitive point, meaning that we are introducing new parameters, right? And why we should force the signal to be a standard normal only to immediately change it. And the reason is a standard normal distribution may not be optimal for the next layer. So forcing all activations into this rigid structure might limit the network's representation power. So how can we resolve that? To solve this, this batch normalization layer basically learns two new parameters: a scale that we denote by gamma, and a shift denoted by beta. So these parameters, gamma and beta, basically shifts and scale the z hat that we computed here, and we are going to call it a BatchNorm output. So what does this mean? Basically means that the network learns the ideal mean and variance for the activation. So in the worst case, when the original distribution was best, the network can simply learn to send the z hat to the previous point that it was. But this batch normalization method helped for a lot of good behavior during the training. It makes the optimization much smoother. And the reason is because the loss landscape will be smoother. And the optimizer can converge more reliably in that case. The learning rates can be chosen to be higher, which means that the training can be faster, significantly faster in a lot of cases. And on the other hand, this basically has a regularization effect. The noise that we introduce with this mini batch statistics has some regularization effect. And it helps to reduce the need for other techniques that does the same regularization, like dropouts that you will see later. And also, this batch normalization even make the dependence on the initial weight choice even less. And this basically, even if your choice of the initialization was not the best, during the training, the batch normalization will somehow help to fix that issue. So even with all of these normalization techniques, as you will see during the course, when we train very deep networks, this issue of vanishing gradients will eventually come at us, especially if we want to go very deep, training very deep neural networks. So one way to resolve that altogether is just to add connections that basically passes the layers. And this way, we basically provide the signal from the before the layer to the after the layer. And this way, it's like it's just a highway, it's a super highway basically that give us, that allows the input of a block of layers, let's say X here, to be added directly to its output So if fx here, this is the layer that acts like a function fx, and then we have the output here will be fx plus x, right? And this basically is an uninterrupted path for the gradients, especially to flow through. Even if a particular block of layer, like for example here in this case, is not useful, the network can easily learn to make its output fx close to 0, right? And it's basically bypass that layer altogether. And the gradient flows backward through the identity connection without any diminish in the value. This was the innovation in the residual network, or in short, ResNet architectures, that allows for training very deep neural networks. One thing that we should be careful when we want to use this technique is to make sure the output of the layer and the input has the same shape. Otherwise, we cannot use this technique. Another thing is this is designed for very deep neural networks. So for shallow networks, this is not necessary and maybe even not helpful. So we conclude the lecture here, but it doesn't mean that there are not other ways to make sure our training is not stable. And during the course, you will see that we will choose multiple or combination of these techniques. And for different architectures, we use different combinations. And these are this will be one of the tools in your disposal as an engineer who does trade-off. For example, in the design, which one of this design for this specific architecture can give you the best result. And this will be one of the points that you have to even maybe try different techniques when you are training in neural network, and at the end choose the one that gives you the best result.